In this situation, a rod is leaning against a vertical wall on a horizontal floor. Here we are required to find the velocity of the end A of the rod when it is inclined at an angle theta with the horizontal. And we are also given that the end B of the rod is pulled with the velocity V0. In this situation, as we have just studied in constrained motion, if we need to relate the velocity of two different points, we are required to relate their displacements. Say the intersection of wall and floor we consider as a reference point, and say point B is located at a distance x and point A is located at a distance y above this reference point. As B is moving away, this velocity V0 we can simply write as dx by dt. Similarly, as A is coming down with the velocity VA, we can simply write VA is equals to minus dy by dt. Here we are using minus dy by dt because y is decreasing with time. Now we can easily relate x and y. If we calculate relation in x and y, it can be simply given as x square plus y square is equals to L square. And if we differentiate this relation with respect to time, we'll get 2x dx by dt plus differentiation of y square is 2y dy by dt, and as L is a constant, its derivative is 0. Now this 2 also gets cancelled out. Dx by dt we can write as v0, the velocity of end B, and dy by dt we can write as minus va. So this becomes x v0 minus y va is equal to 0. So from here we can directly get the value of VA is equals to x by y into V0, and in this triangle x upon y we can directly write as cot theta. So this becomes V0 cot theta. This is the velocity of end A when rod is leaning at an angle theta with the horizontal. This is the answer for our problem. Let's discuss an alternative method to handle the similar problem. Here we are required to find the velocity of end A, this VA with which this end A is coming down. In this method, here we observe 2 points of which the separation remains constant when the system is moving. Here we can say when this rod is sliding like this, the separation between end A and end B always remains equals to L. So we can say we find out the velocity of this end B along the length of this rod. If this angle is theta, this velocity will be V0 cos theta. And if this angle is theta, this must be 90 minus theta. So the velocity of end A along the length of rod can be written as VA cos of 90 minus theta, that will be VA sin theta. So here we can say while the rod is in motion, A is moving toward B at velocity VA sin theta and B is moving away from A at V0 cos theta. And as the length of the rod is constant, their separation is not going to be changed. So if we find out the velocity of A with respect to B along the line joining, it has to be equal to 0. That means the two must move with the same velocity along the length. Then only the length or the separation between the 2 points must remain constant. So in this situation we can say for L to be constant, we must use VA sin theta is equals to V0 cos theta. So in this situation, the value of VA we can directly get it as V0 cos theta by sin theta, that is V0 cot theta. Here you can say just by equating velocity components along the length of the rod, or more precisely equating velocity components along the line joining the two particles, we are directly getting the result. Along with this, we also write down a note just to make this as a concept, keeping in our mind that for 2 points, if their separation is constant, then you can write during motion their velocity components along the line joining these points always remain equal. Always keep this in mind that if 2 points are having constant separation, then no matter whichever be the way they are moving, their velocity components along the line joining the particles must be equal. Then only we can say their separation remains constant. There's also a very important concept going to be used in several applications.